trying to quiet the computer before it says that. All right. So, okay, so we're recording. All right. Okay, we're entering part 4 of the class out of 5 parts. All right. So, the next part deals with lessons 24 through 32. We're going to start off inference, especially point and interval estimates. All right. So that's going to be part 4 of the class. The homework for that will be due the week before Thanksgiving break. Although if you really need Thanksgiving break, email me and we can talk about it. But we'd like to get that thing done before Thanksgiving break. All right. And then part 5 will be after the break, covering this last piece over here. But as you can see, it gets very intense. Notice here, like December 7th, very intense. Okay. All right. So we're entering part 4, lessons 24 through 32. We have much to do today. All right. Any questions before we proceed? Again, questions in chat. Okay. So much to do today. Questions in chat. All right. So let's begin. All right. Hi, everyone. In part 4 of our class, we're going to estimate population parameters, which could be something like a population mean, a population standard deviation, a population variance, or as we'll see, a population proportion or probability. To estimate these population parameters, we could use a point estimate, which is a single value, or an interval estimate. That's where confidence intervals come in. So in part 4, and later in part 5 of our class, we're going to be dealing with inferential statistics, which is the magical, applied, and controversial part of our class. This is the part where pure mathematicians get very nervous, but it's what you see a lot of in real life. This is what a politician with a pollster would really care about. So back in lesson 1, we talked about the overall scheme of the class. So where are we in this class? Well, first of all, we talked about designing an experiment, and in particular, defining a population of interest. For example, do you care about all adult Americans in the end? Do you care about all registered voters in California because you're doing a political poll? What is the population of interest of size big N? And then, step 2, collecting data. Now, I didn't have you go out and grab random students. That would be inappropriate, especially nowadays. But we talked about schemes such as simple random sampling, systematic sampling. We talked about random number generation, which could help you figure out who to poll, and other methods. In part 3, describing data, and that's descriptive statistics. So from a population, let's say you draw a sample. Okay, a sample of size little n, maybe 1,000 people for a political poll, okay, or maybe a scientific study, such as maybe we're gathering a sample to see what their situation is with antibodies for coronavirus. Or it could be in a factory. We're testing products for quality control. These could be pills, for example. But anyway, in this sample, we can get sample data, presumably quickly. That's the idea behind drawing a sample, instead of doing an outright census for the population. So within the sample, we might be able to ask voters, are you for a candidate or against a candidate? We can ask, what's your weight? That might be a bit rude, but we can ask, what's your weight or what's your age? Or more politely, we can grab a pill off the assembly line and take its weight or mass. But we can get data for our sample, and we can describe this data by using things like histograms, dot plots, pie charts, things like that. And that was what we did early on in the course. Now, we're going to interpret the data based on the sample. So based on the sample data of size little n, what can we try to infer about the overall population of size big N? So if we take a random sample of 1,000 registered voters in California, and we want to ask them, do you have a favorable or unfavorable view of President Trump? Well, based on the sample, we can try to infer the actual population parameter of interest. What is the proportion of registered voters in California who have a favorable or maybe unfavorable opinion of President Trump? Bear in mind, there may be other categories, favorable, unfavorable, or maybe other or undecided. Although with President Trump, there don't seem to be too many people in the middle. Inferential statistics, the science of interpreting data. Very controversial, but very useful. What can a sample tell us about the population from which it is drawn? So that is going to be our key topic for the next several lessons.
Okay, so that was an intro. Okay, any questions? So this is where the art comes in, inferential statistics.
Everyone, we're now going to talk about point estimates for population parameters. If a single value is used to estimate a population parameter, we call that value a point estimate for that parameter. So for example, if I were to ask you, what was the average or mean number of Netflix videos watched last week by an American adult, if you consider the population of all American adults, perhaps those who own Netflix? You might say 100 videos. I didn't say it was accurate, but that could be your point estimate for the mean number of Netflix videos watched last week by American adults who have Netflix. All right. Now, instead of just guessing, let's say that we draw a sample from a population. Well, what would make sense? It would make sense that based on these sample statistics, we're going to infer the values of these population parameters. So we use sample statistics to estimate population parameters. We will use the sample mean, x bar, as a point estimate for the population mean, mu. And this would make sense. So let's say you actually took a random sample of 800 random American adults who have Netflix. And you ask each of them, how many videos did you watch last week on Netflix? Maybe you actually get a sample mean of 100 videos. I'd be a bit surprised. Maybe not that surprising, but let's say that the sample mean was, in fact, 100 videos. Then that would be your best point estimate for the population mean, mu. Likewise, we will use the sample standard deviation, S, as a point estimate for the population standard deviation, sigma. So perhaps more than anything else, you have to remember what these notations stand for. The sample standard deviation is used to estimate the population standard deviation. We're inferring the value of sigma based on the value of S. And likewise, we will use the sample variance, S squared, as a point estimate for the population variance, sigma squared. So these sample statistics will typically be used as point estimates for these population parameters. So let's review these principles. All right. Example 1. A large lecture class takes a test. 5 of the tests are randomly selected and graded. The grader reports that the sample mean is 75 points, the sample standard deviation is 15 points, and the sample variance is 225 square points. So X bar is 75 points, S is 15 points, and S squared is 225 square points. I know that's a weird unit. Well, what would be a good point estimate for the population mean of test scores for the entire class? What's a point estimate for the population standard deviation of test scores for the entire class? And what's a point estimate for the population variance of test scores for the entire class after all the tests are eventually graded? Well, it would make sense that our best point estimate for mu will be X bar, 75 points. It makes sense that the best point estimate for sigma, the population standard deviation, would be S, 15 points. And our best point estimate for the population variance, sigma squared, would be S squared, 225 square points. So again, we're going to use these sample statistics as our best point estimates for these population parameters. So to quickly review, the point estimate for the population mean is the sample mean, X bar, or 75 points. the best point estimate for the population standard deviation is the sample standard deviation, S, or 15 points. And the best point estimate for the population variance is the sample variance, S squared, or 225 square points. Again, X bar is our best estimate for mu, S is our best estimate for sigma, S squared is our best estimate for sigma squared. All right. And why is it that the sample mean is the best point estimate for the population mean, or one of the reasons? Well, because it turns out that the sample mean is an unbiased estimator for the population mean. Here's a bit of theory. Don't freak out too much about it. A sample statistic is an unbiased estimator for a population parameter, such as mu, when the expected value of the sample statistic, like X bar, the sample mean, is the value of the population parameter, mu, the population mean. So again, a key reason why we use the sample mean as a point estimate for the population mean is that the sample mean is an unbiased estimator for the population mean. So in short, although you need to understand the theory behind this to understand this, E of X bar equals mu. The expected value of X bar as a random variable is mu, the population mean. Now, what does that mean? What does this signify? All right, well, consider a class, okay? So let's say here's a big lecture hall of 1,000 students. Consider all possible samples of size 5 from the class. Now, of course, this sample could be spread out at various points throughout the class, but just for convenience, let's say that one sample of size 5 looks like that. Let's say another sample of size 5 looks like that. Let's say another sample of size 5 looks like that. Remember that these samples will overlap when you consider all possible samples of size 5. So if you consider the sample mean you get from this sample of 5 students, you consider the sample mean from this sample of 5 students, you consider the sample mean from this sample of 5 students. You get these various values for X bar. If you consider all of the sample means from all possible samples of size 5, and if you line them all up and take their average, the average for those sample means, the expected value of the sample means, will be mu, the actual population mean test score for the overall class. So that means that this sample mean as a point estimate for the population mean is an unbiased estimator, meaning that unbiased estimators, like the sample mean for the population mean, they do not have a tendency to overestimate or underestimate the population parameter. They tend to target that parameter. X bar tends to target mu. There's no tendency for it to waver on the low side or the high side. There's no bias. X bar tends to target mu. And that's very helpful. Now, in general, or more generally, it turns out that, yes, X bar is an unbiased estimator for mu. S squared is an unbiased estimator for sigma squared. It actually turns out that S is technically not an unbiased estimator for sigma, but it's typically good enough, especially for large sample sizes. Things are better when the sample size is bigger. All right, so we've talked about population parameters, the sample statistics we use as point estimates for those population parameters, and also the reason why we like some of these sample statistics as our best point estimates. It helps for them to be unbiased. S isn't quite an unbiased estimator for sigma, but it's close enough. Next, we're going to talk about the population parameter P, which represents a population proportion or probability, and its corresponding point estimate, P hat, a sample proportion. That's for next time.
All right, any questions so far? Because we're going to look at another parameter in the next video. Any questions? Any questions? All right, we're doing point estimates right now, okay.
Hi everyone, last time we talked about using sample statistics as point estimates for population parameters. We used the sample mean X bar as the best point estimate for the population mean, nu. We used the sample standard deviation, S, as a good point estimate for the population standard deviation, sigma. And we used the sample variance, S squared, as the best point estimate for the population variance, sigma squared. Now, we're going to use p hat, a sample proportion or probability, to estimate p, a population proportion or probability. All right. So this is now the fourth column in our table. We're going to let p denote a population proportion, although it could also represent a probability, such as the success probability p from a binomial NP distribution. So this is the part of the class that's of interest to politicians and also to gamblers. Politicians will look at things in terms of population proportions, proportions of voters that support the candidate or politician, and gamblers will look at probabilities that they want to estimate. Now, before, I would give you a binomial NP distribution, and you would calculate probabilities or manipulate probabilities based on that distribution, maybe even approximate it with a normal distribution. But now we're going to do the reverse. Given a sample size or number of trials, little n, I'm going to have you perform a random experiment. I could give you a coin, and we're not going to assume it's a fair coin. It might be a magician's coin. And I might say, hey, flip this coin a whole bunch of times, and based on that random experiment, let's estimate the value of p, the probability that the coin comes up heads, let's say. So we're going to reverse the problem. We're going to ask the inference question. Based on sample data, what can we infer about a population parameter, like this probability in a binomial NP distribution? So to reiterate, we can think of p hat as representing a sample proportion to estimate a population proportion or probability. So remember, a success is a property that we are interested in. So for example, a politician would say that a success is a voter who is going to vote for the politician. A gambler might say, hey, I like heads. A success is when this coin comes up heads. So let's look at it from the politician's perspective. Let's say that the politician wants to know the proportion of voters, registered voters, or likely voters maybe, in his or her state, who will vote for that politician. If n is the sample size, like the number of people in a poll, let's say of 800 registered voters in California, and if x is the number of successes in the sample, so the number of people in the poll who support the politician, then the sample proportion of successes is given by p hat. The sample proportion equals x over n, the number of successes divided by the sample size, which makes sense, as we'll see. If you're a gambler, and if we give you a coin, a magician's coin, so we don't know if it's a fair coin or not, and let's say that you like heads. Heads is your favorite side of the coin, and you want to estimate p, the probability that the coin comes up heads. So p is the actual physical probability that the coin comes up heads. Well, you could flip the coin a whole bunch of times and estimate p by using a point estimate, p hat. If n is the number of trials in a binomial experiment, n here would be the number of flips of the coin. And if x is the number of successful trials, the number of times the coin comes up heads in that experiment, then our point estimate for p hat, this p is the success probability per trial in a binomial NP distribution. Our point estimate p hat is given by x over n. The same idea as before. It's the number of successes in our experiment over the number of trials. It's the same basic idea. So this would be the sample proportion of successes among the n trials. In both cases, x over n. P hat is x over n. So let's apply this idea to an example with two parts. Well, really two examples. Let's apply this idea to two examples, both with two parts. All right, so in example 2, after a national presidential election, a random sample of 500 people who voted in the election are interviewed. 300 of the 500 interviewees voted for the Purple Party candidate. And let's assume they're telling the truth. Actually, and we've seen this before, maybe the Purple Party candidate won, and then the interviewees in the poll might be going, I might be in trouble if I say I didn't vote for the winner. But let's set that aside. Let's assume that these interviewees are telling the truth. 300 of the 500 interviewees voted for the Purple Party candidate. Part A, find p hat, the sample proportion of the interviewed voters, the interviewees, who voted for the Purple Party candidate. Part B, what is the point estimate for the actual population proportion of voters in the election who voted for the Purple Party candidate? So maybe this is the result of an exit poll, and maybe we don't actually know what the results will ultimately be for this election. This could be an exit poll. All right, part A, find p hat, the sample proportion of the interviewed voters who voted for the Purple Party candidate. Well, it's given by x over n. P hat is given by x over n. The number of successes, 300, that's the number of people who said they voted for the Purple Party candidate. Let's assume they did vote for the Purple Party candidate. So from the Purple candidate's perspective, a success is a voter who voted for him or her. We divide that by n, which was the number of interviewees. We're dividing by little n. Big N could be in the millions, but little n is 500. X over n, 300 over 500, or 0.6. That's our value for p hat, the sample proportion of the interviewed voters who voted for the Purple candidate. So basically, in this exit poll, the Purple candidate is getting 60% of the vote in this exit poll, But then, based on that exit poll, what is a point estimate for the population proportion of voters in the election who voted for the Purple candidate? So this is the actual population proportion among the millions of voters who voted in the election. We weren't able to do a sample. We weren't able to do a census, so instead we looked at a sample. All right. What is a point estimate for the population proportion of voters in the election who voted for the Purple Party candidate? Well, it's going to be p hat, the 0.6. If the exit poll said that 60% of the voters voted for the candidate, because 60% of the voters in the exit poll voted for the Purple candidate, then we're going to infer from that. That 60% of the voters who voted in the election voted for the Purple Party candidate. Later on, we'll talk about margin of error and uncertainty and sampling error and all that. But our best point estimate, based on the exit poll here, is 60%, or 0.6. That's our best point estimate for the actual population proportion of voters in the election who voted purple. And in the end, in the election, that's what's going to matter. So, for example, if the purple candidate gets 60% in the exit poll, but only gets 40% of the vote in a two-way race, then the Purple Party candidate isn't going to be so happy with the result of the election. By the way, that probably means your poll was terrible. I mentioned before sampling error and margin of error. We're going to talk about those issues next. And we're also going to talk about confidence intervals and interval estimates. What if you're allowed not just a point estimate for a population parameter, but a whole interval or range of values? That's next time.
Any questions before we go on? Any questions? Any questions? All right. Just know that in the United States, the Electoral College matters, right? That determines the president. All right.
Hi, everyone. We're finishing up lesson 24 on point estimates of parameters. I almost forgot example 3 on sample proportions and probabilities, our coins example. So let's say you're given a magician's coin and you don't know if it's fair or not. So how would you estimate the probability that this coin comes up heads? Let's say heads is your favorite side. It represents a coin being a success. It comes up heads. You like faces. So you take this coin and you flip it 1,000 times. It comes up heads 510 times out of the 1,000. So out of the 1,000 times, that's n, the number of trials, you get x successes, 510. That's the number of heads, because you're counting heads. Those are successes. Part A, find p hat, the sample proportion of heads among the 1,000 coin flips. And then part B, what is a point estimate for the probability that the coin comes up heads on one flip? Well, I hope you see that our value for p hat will be our point estimate for p. P is the probability that the coin comes up heads. P is the probability the coin comes up heads. Again, it's a magician's coin. It's not necessarily fair. Or at the very least, we don't assume that the coin is fair. Actually, in real life, many coins, in fact, you could say all coins, are not perfectly fair. So what's our best guess as to the actual proportion, or it's a probability this time, the probability that the coin comes up heads? The idea that if you flip the coin infinitely many times, what's the proportion of times it would come up heads? All right, so the solution. P hat, the sample proportion of heads, would be x over n. The number of successes, the number of heads was 510, over the number of trials, 1,000, that's 0.51. So you got 51% heads among the 1,000 coin flips. And that would be our best point estimate for P, the actual probability the coin comes up heads on a flip. Again, 0.51. P hat is our best point estimate for P. This sample proportion of heads is our best point estimate for the actual probability the coin comes up heads, which again can be thought of as the proportion of times or flips the coin comes up heads on infinitely many flips. So we can frame P and P hat problems in terms of sample proportions or probabilities. In either case, we take as P hat our sample proportion, the number of successes in our experiment over the number of trials, or the sample size in our experiment. Next up, as promised, we're going to talk about issues of error. Sampling error, margins of error. If you get 51% heads, does that mean that the coin couldn't be fair? Or is this just due to sampling error? We'll ask those kinds of questions next time.
Okay, so that's the kind of question we're going to ask. Just because the coin comes up heads 51% of the time, are we eliminating the possibility that the coin could be fair? That's kind of the idea. Any questions about P and P hat, right? So P hat is to P as X bar is to mu, right? Questions? All right, questions in chat?
Hi, everyone. We're going to start lesson 25 on interval estimates. We're going to call these confidence interval estimates of population parameters. So what if, instead of a single value, a point estimate, what if we're allowed a whole range of guesses, not just a single point estimate? First off, let's discuss the idea of sampling error. All right, so here's the idea. We have a population, maybe test scores in a big lecture class. And from this, we draw a sample. All right, well, this sample, it could be 5 students, let's say, and their test scores. A sample often does not represent the population or probability perfectly, and this often leads to sampling error. So although we hope this random sample, who knows, it could be a systematic sample for that matter, who knows if this sample really is that representative of the overall population? We hope it'll be. We believe it should be, but it may not be representative of the overall population, and it probably is not perfectly representative of the overall population. What's going on with 5 students may not be exactly what's happening with 1,000 students. Now, a point estimate, typically a sample statistic, such as the sample mean, x bar, may or may not equal the true value of the population parameter that's trying to estimate. So for example, if we take a sample mean for this sample of 5 students, we hope that it'll be close to the population mean for all 1,000 students and their test scores, but the odds are it's probably not exactly on the mark. We hope it'll be close, but we do expect some sampling error. All right. So again, on sampling error, example 1, A, the population mean for a class exam could be 75 points. Okay, so it turns out that the mean for all the scores may end up being 75 points after all the tests are graded. But the sample mean, when only 5 tests were graded from a random sample, the 5 tests may have only had a sample mean of 74 points. But you see how this is quite possible, how overall the class mean may be 75 points, but the sample of 5 students happened to average 74 points. You can see how this is quite possible. So it's not surprising at all that maybe the population mean is 75 points, but the sample mean was only 74 points. That would not be so shocking. Later on, we'll see cases where it would be shocking. For example, if the sample mean were 20 points, then perhaps the discrepancy would be shocking. Then it's probably not just chalked up to sampling error. Part B, a fair coin may come up heads 51 times in 100 flips. So you can imagine this here as being, I guess, infinitely many possible alternate universes where we're flipping this coin. All right, well, if it's a fair coin, then P, the probability of heads, will be 0.5. Let's say we do have a perfectly fair coin. Not that one really exists, but let's assume that we have a perfectly fair coin. Now, we don't have time to toss it or flip it infinitely many times, but we may be able to flip it 100 times if we don't have much else to do. So this here represents the 100 trials, the 100 flips. It's kind of like a sample. We can think of it as a sample, in fact, a sampling of flips. So here, p hat, the sample proportion, if we're getting 51 heads out of 100 flips and heads is success, well, the sample proportion would then be 51 over 100 or 0.51. That would be our p hat. And it would be our best point estimate for p. Maybe we don't know what p is yet. Maybe we don't know yet that it's a fair coin. But again, you can see how this is quite possible. How if we had a perfectly fair coin, if anything, that's the hard part to conceive of. If we had a perfectly fair coin, then it's not so shocking that it would come up heads 51 times out of 100 in our 100 trials, where p hat is 0.51. So sampling error is something that comes naturally. Something like this should not be shocking. Our sample statistics, the information from our sample, may not be perfectly reflective of what's happening in the overall population, or what's actually happening with, in this case, the coin. Next, we're going to talk more about interval estimates. The idea that, well, let's see, if we have a sample proportion of 0.51, if we got 51% heads, well, 51% might be our best guess for what p is up here, 0.51. But if we were allowed a range of values, an interval of values, what would be reasonable? That's next time.
Okay, so next questions, because next we're going to talk about interval estimates, not just point estimates, but interval estimates. All right. Because remember, let's say we don't assume we have a fair coin. Then if you flip the coin, you get 51 heads and 100 flips, your best estimate for P would be 0.51 if you didn't know it was a fair coin. All right, interval estimates.
Hi, everyone. We're continuing with lesson 25. Before we talked about single value point estimates for population parameters, now we're going to talk about interval estimates. Later on, we'll call these confidence intervals. To account for sampling error, we'll provide a range of values called an interval estimate for a population parameter, such as a population mean. So instead of a single value, we'll offer a range of values. Example 2. Let's say a lecture class takes an exam, a big lecture hall class, and we want an interval estimate for mu, the population mean of exam scores in the class. So let's say that I'm the professor of the class. I'm looking around at these 1,000 students taking the test. They're sweating. I notice they're sweating, and I'm wondering how they're going to do. So after the end of the exam, I talked to my TA, Igor, who's going to help grade the exams. Now, it may take several days for Igor to grade all the exams, but I might be curious. Well, that night, how well did the class do? I want a sense of how well the class did. So I'd like to get an estimate for the population mean for the class, the population mean of the 1,000 exam scores in the class. Now, Igor does not have time to grade all 1,000 exams tonight, but Igor could take a random sample of 5 tests, grade those, and give me point and interval estimates for mu based on his sample mean, x bar, and also some measure of spread, as we'll see. So Igor takes the 1,000 exams, throws them up in the air. I duck or I hide under a desk, and Igor randomly selects 5 exams to grade. Remember, just grabbing the top 5 exams off the stack might lead to a biased estimate. So Igor takes a random sample of 5 exams, and Igor grades them. And based on the sample statistics, Igor could give me an interval estimate for mu, because Igor knows some statistics. So a random sample of 5 exams is selected and graded. Our interval estimate for mu could be this interval, from 70 points to 78 points below. So I ask Igor, give me an interval estimate for how well the class did, the population mean for the class, the mean for all 1,000 students. Well, based on his sample and his sample statistics, Igor could say, Master, I'm getting an interval estimate of between 70 points and 78 points. So if I had to guess, I'd guess that the overall population mean for the class will be somewhere between 70 points and 78 points based on what I'm seeing on my sample. And by the way, Igor could also claim that his point estimate for the population mean is the sample mean, 74 points. How do you think the sample mean here compares to these two numbers? Think about that. All right. By the way, the 70 and the 78, those are 70 points and 78 points. Those are referred to as the limits of the interval estimate. 70 points is the lower limit. 78 points is the upper limit. And how do we arrive at the sample mean? Given the interval, or given the limits of the interval, how could we figure out the sample mean? Well, what's the relationship? The 74 is the average of the two limits, the two endpoints of the interval. The sample mean, x bar, is at the center or midpoint of the interval. It's the average of the lower limit and the upper limit. In this case, the 70 points and the 78 points is the average of these two values. And how do you take the average of two values? You add them up and divide by 2. And it has the same unit as either limit. You add up 70 and 78, divide the sum by 2, and you get 74 points. That's the sample mean. In this class, whenever we do an interval estimate for mu, a population mean, the sample mean, the point estimate, will be the midpoint. It'll be right in the center of that interval estimate. This will also be true for p hat, the sample proportion, if we're doing an interval estimate for p, a population proportion or probability. However, this will not be true of interval estimates for sigma or sigma squared. So to reiterate, this interval estimate is symmetric about the point estimate, x bar, or 74 points. The 74 points, the sample mean, x bar, is right in the middle, the midpoint of the interval estimate. But this will not always be the case. It is true for p hat and p, and for x bar and mu, our estimation for mu. But when we estimate standard deviations and variances, well, actually, we cannot appeal to symmetry. It turns out, for example, that an interval estimate for variance, at least the kinds that we're going to develop in this class, those intervals will not be symmetric around the sample variance. Same for standard deviations. But for x bar as an estimate of mu, for p hat as an estimate of p, then yes, these will always be at the center of corresponding interval estimates. Next up, we're going to discuss the margin of error, which is basically this here. It's the distance between the sample mean and either endpoint, either limit. That's the margin of error, which we hear about a lot. And we'll talk about that next.
Yeah. Questions, because certainly when you're hearing about polls, and statisticians wish that that these news networks would report the margin of error more, for example. Questions. Although they're talking about proportion margin of errors, here for x bar is for means. So we can talk about margins of errors for means, proportions. All right, moving on.
Hi, everyone. We're continuing with lesson 25, and we're talking about the relationship between point estimates and interval estimates for a population parameter. Over here, you can see that with an interval estimate for mu, or an interval estimate for p, the corresponding point estimates at x bar or at p hat will be at the center of the corresponding interval. So these interval estimates will be symmetric about their point estimates. That's true with interval estimates for mu and for p, though not for sigma or sigma squared. In both cases, the margin of error is this distance between the point estimate, for example, the sample mean, and either limit of the interval. So try to think of 3 ways that you could calculate the margin of error. If I gave you the lower limit and the upper limit of a confidence interval, basically the confidence interval, in this case, a confidence interval for mu, how could you calculate the margin of error? Think of 3 ways you can calculate the margin of error, which I'm denoting by E over here. Well, let's go through these. And also, we will interpret the margin of error. Okay, so in example 2, we estimated the population mean of exam scores in a class. Our point estimate was the sample mean. X bar was 74 points. Or you could have calculated that from the interval, the limits of the interval. You could take the average of the 2 limits and get the point estimate, the sample mean. Our interval estimate is symmetric about the point estimate, 74 points, because this is an interval estimate for mu or for p. We have symmetry in those cases, though not for sigma or sigma squared. All right, now in example 3, we're talking about the idea of margin of error, which is this distance between the point estimate and either limit. Well, there are 3 ways to do it. In this example, you can take the upper limit. So you do this in red. You can do the upper limit minus x bar, or 78 minus 74. So you could go 78 minus 74. That gives 4 points. That gives you the margin of error, which is 4 points. Also, you can take x bar minus the lower limit. You can take 74 minus 70. That gives you 4 points. Again, is that same margin of error. And we have symmetry of this interval about the sample mean, the point estimate. A third way you can do this is that you can take the overall width. The overall width over here is 8 points. And you can cut that in half. So you can take the upper limit minus the lower limit, the entire width of the interval, which is 78 minus 70, or 8 points, divide by 2, you get 4 points. So there are 3 ways that you can figure out the margin of error, given the limits and or the sample mean. Now, the interval estimate here that we have for this population mean mu, this mean test score for the class overall, which we don't know yet, this can be written in terms of the sample mean, the point estimate, and the margin of error E. And this is because we have symmetry. So when we're doing interval estimates for mu or P, where we have symmetry, we can use that in order to more accessibly represent the confidence interval, in order for it to make more sense. So we're saying here that the population mean is basically the sample mean, give or take the margin of error. So the population mean, we're saying informally that it's 74 points, the sample mean, give or take 4 points. The sample mean, give or take 4 points. So realistically, the population mean could be as low as 70 points or as high as 78 points. It could be anything in between. Now, I need to clarify something. This notation, this plus or minus notation, because before, when you use this in your algebra classes, you may have used it in a different way, like in the quadratic formula. In the quadratic formula, when you saw plus or minus, you usually took both cases and accepted both cases, and there were two answers to your problem. But here, the plus minus means something different. It means give or take, basically. So our confidence interval for the population mean consists of 70, 78, and everything in between. Now, don't freak out at the issue of parentheses versus brackets. The way I'm writing it, it looks like an open interval. And this is pretty standard in statistics, but you could just as well write it as a closed interval. So we could say that the population mean could be realistically 70 points or 78 points or anything in between. Bear in mind that when you're doing things like using the quadratic formula back in your algebra class, you got two answers, and that was it, just two numbers. Bear in mind that the confidence interval here does not just contain two numbers, the 70 points and the 78 points. Here I'm kind of using brackets, sort of. It also picks up every number in between. So we're using this plus minus notation a bit differently from before in your algebra classes. Now, what are some ways that you can interpret this margin of error, 4 points? I'm going to go back up here. The margin of error for a symmetric interval estimate. Again, this applies to interval estimates we're going to do in this class for mu, a population mean, or P, a population proportion or probability. Our interval estimates will be symmetric about their corresponding point estimates, which will not be the case for sigma or sigma squared. But for a symmetric interval estimate, the margin of error, denoted by E, is the distance between the point estimate, in this case x bar, and either limit. That's why we could calculate it by doing either 78 minus 74 points or 74 minus 70 points. It's basically the difference between x bar and either limit, where you take the larger minus the smaller. The margin of error is always positive. So the margin of error, again, denoted by E, is the distance between the point estimate and either limit. You go larger minus smaller. Also, it is half the width of the entire interval. That's where we took the entire width of 8 units and divided by 2. And that gave us the 4 points as well. Okay. Also, and this is somewhat new, it is the maximum likely distance between the point estimate and the true value of the population parameter being estimated. I just hinted at this before. What we're saying here is this. Remember that this interval estimate is an estimate for mu, a population mean. We're saying that we believe that the population mean is between 70 points and 78 points. And the point estimate happened to be at the sample mean, 74 points. But really what we're saying here is that we believe that the population mean is within 4 points of the sample mean, the point estimate. Okay, but at most we'd expect mu to be at most 4 points away from x bar. So at most mu could be 78 points realistically, or as low as 70 points realistically, or it could be anything in the middle. It could match up with the sample mean, although that's unlikely. Again, the margin of error, which in this case is 4 points, is the maximum likely distance between the point estimate, x bar, and the true value of mu, the population parameter we're interested in and that we're estimating. So we're saying that we think that mu is within 4 points of x bar, which is basically what this notation kind of hints at. Our estimate for the population mean is the sample mean, the point estimate, x bar, give or take the margin of error. And sometimes we prefer this form. In the homework, I'll make clear which form I prefer. This interval form where you indicate the limits of the interval, or this form where you indicate the central point estimate and the margin of error. The population parameter of interest could be the point estimate, give or take the margin of error. And again, this form would apply only to symmetric intervals. In this class, that means an interval for mu or an interval for p, but not sigma or sigma squared. Next, we're going to talk about why these interval estimates are often called confidence intervals, and that's next time.
Okay. Any questions? Any questions? So here you see we can express a confidence interval in terms of the point estimate and the margin of error. Questions? Questions? Next up, why do we call these confidence intervals that we're going to develop?
Hi everyone, we're continuing with lesson 25, and we're going to explain why these interval estimates for population parameters, such as a population mean mu, are going to be called confidence intervals, or CIs. That would be my acronym for confidence interval. Now remember, let's say that our TA, Igor, tells us that he believes that the population mean test score for the 1,000 students is somewhere between 70 points and 78 points. That's an interval estimate. Before, I might have labeled this axis with mu. I'm labeling it with points because that's the unit. Actually, I'm not going to label the axis with mu anymore because mu is a value that we're targeting. Here, I just wanted to remind you that these were possible values for mu. Okay, but Igor says our confidence interval for mu is between 70 points and 78 points. It's the interval consisting of these values. And then I might ask Igor, how confident are you? How sure are you? Back in the game show, Who Wants to Be a Millionaire? That was a famous question that was asked. How sure are you? When you asked your phone a friend how confident he or she was that an option really was an answer. How sure is Igor that this contains the true population mean, the thing we're trying to estimate? So that confidence level, how sure are you, is a probability that is often expressed as a percent. And when we attach a confidence interval to an interval estimate, we have a confidence interval estimate for that parameter. Okay, and of course the idea is that the interval estimate should be likely to contain the value of the parameter. In fact, the most common confidence level is 95%. It should be a high probability, like 95%. There's no point in having a 10% confidence interval. Okay, so the confidence level is the probability that the confidence interval contains the true value of the parameter. The most commonly used confidence level, again, is 95%. And this is the typically assumed confidence level in published studies and news reports. In fact, many statisticians are irritated by the fact that when polls and other studies are reported by the news media might report the margin of error, like in a poll, for example, but the news media almost never tells the audience, hey, the confidence level is 95%.
Confidence level, not
communist. That is
communist.
typically the assumed confidence level. You should know that as a news viewer. Granted, the news is not very pleasant to watch today. All right. So some examples of confidence levels and related confidence intervals. Let mu be the population mean IQ score of American adults. IQ is meant to measure intelligence. Bear in mind, I'm not saying that I have much confidence in this kind of measurement, but these are common examples used in statistics books. Let's say a psychology professor wants to estimate mu, the population mean IQ score of American adults. So the professor analyzes a sample of American adult IQs, a random sample. Let's say that the sample mean for the sample, x bar, is 101 points. And the professor also finds the sample standard deviation or variance. You do need a measure of spread, as it turns out. So based on this sample data, well, I should say sample statistics. Based on these sample statistics, which are based on the sample data, the professor can construct a 95% confidence interval for mu, the population mean IQ score for all American adults. And let's say that this professor, maybe with the help of software, Excel or StatCrunch, let's say that the professor finds that the 95% confidence interval using the professor's methods will go between 98 points and 104 points. These are the limits of the 95% confidence interval. The interval consists of these values and all values in between. Technically, I'm using a bracket interpretation of this interval, but don't freak out about it. It doesn't matter if you put brackets or parentheses in this class. Okay, technically, if you include endpoints, you should put brackets. All right, let's now interpret this confidence interval, this CI. So here's the interpretation. We are 95% confident that this interval contains the population mean IQ score of American adults. So we're 95% confident that this interval contains mu. But of course, when stating this interpretation using proper English to a layperson, you want to avoid the Greek letters. You want to write out what mu is. Mu is the population mean IQ score of American adults. So you should write that out. If you're rushing on a test, you could at the very least do something like a star here and point to that at the very least. But you should write out what mu represents. You're writing out an interpretation for a layperson who doesn't really know statistics. Okay, so that's basically the typical American adult. Now, some books, such as Mario Triola's book, object to saying that there is a 95% chance that mu falls in the confidence interval. So there's some semantic objection to this term falls in. I don't have such a strong objection, but here's Triola's argument. Triola's argument is kind of a Zen argument. Triola is basically saying that mu, the population mean, is a fixed but unknown target. So there is a population mean IQ score for American adults. Granted, it might depend on the type of test or whatever, but let's say that mu is a particular fixed but unknown target. There is a population mean IQ score for American adults. We just don't know what it is. We might not ever know what it is at any given moment. But let's say that mu is a fixed but unknown target. Then mu isn't really falling anywhere. So if you consider the variety of confidence intervals that you might construct, let's say that you have different psychology professors who take different samples. Maybe you get this confidence interval from 98 points to 104 points. Notice that the sample mean lies in the middle, 101 points. In fact, that was stated in the previous example. This was the confidence interval, and the sample mean, of course, is right in the middle because we have symmetry about the sample mean for the confidence interval for mu. So this was our psychology professor's interval. But maybe a colleague across the country uses a different sample and gets this confidence interval, maybe going from, I don't know, 95 points to 100.5 points. Maybe another colleague gets this confidence interval. And maybe another colleague gets this confidence interval. Now let's say hypothetically, mu turns out to be 100 points. Theoretically, a number of IQ tests are structured so that 100 points is meant to be the mean IQ score. But that's rather hard to calibrate though. But let's say that in fact, the true value for the population mean is 100 points. Well then, your colleague over here, the one who gets the confidence interval between 101 points and 105 points, that one misses the mark. It turns out this one misses mu. It doesn't mean that your colleague is an idiot or doesn't know statistics. Maybe it was just a matter of extreme sampling error. I mean, we're allowing for some sampling error, but maybe this colleague was just unlucky. This colleague just happened to miss the mark. So mu is a fixed but unknown target. It's not really falling anywhere. The question is, does a confidence interval contain the actual value of mu or not? And again, perhaps we may never know what the true value of mu is. At least in an election, we know what the result of an election is. We think, if the votes have been tabulated accurately. That's a big if. And by the way, what's a way that we can interpret the confidence level? I was saying here that the professor was constructing a 95% confidence interval for mu, the population mean IQ score of American adults. Well, what's one interpretation for 95%? Well, one is that when the confidence interval is constructed, then in principle, there is a 95% chance, we are 95% confident that this confidence interval will in fact contain the true value for mu. If mu is in fact 100 points, then this confidence interval up here is good. It works in the sense that it does contain the true value of mu, 100 points. Whereas this confidence interval, although it might have been intelligently constructed, it may have just missed the mark. Maybe it was just a bad sample for some reason. And maybe not because of bad design, it was just a bad sample. The professor was unlucky. Well, one interpretation for a 95% confidence interval is that if you imagine many confidence intervals being constructed, let's say 100 of them, and they're all 95% confidence intervals, and let's assume they're all constructed appropriately. That's a big assumption, though. Let's assume that you construct 100 confidence intervals constructed appropriately based on 100 varied samples. So you might have 100 colleagues across the country who took 100 random samples. They could have even had overlapping people in them. And these 100 confidence intervals are constructed. If these are all appropriately constructed 95% confidence intervals, then about 95% of these, or about 95 or 100 out of 100, should contain the true population mean, 100 points, and about 5% will not. So here's a freaky thing about statistics. If the methods are applied appropriately, statistics predicts its own failure rate. So there's a certain humility here. Statistics admits that you might get a bad interval sometimes. So there's a humility there. But there's an arrogance in that it predicts its own failure rate. It predicts that about 95% of these confidence intervals will contain the true value of mu, and about 5% won't. So there is some arrogance there. All right. Now, if you don't believe me, let's take a look at this applet. It's the Rosman chance applet from a couple of professors at Cal Poly San Luis Obispo.
By the way, I want to send you the link to this. Let me grab this here. I'll also email it to you at some point.
In fact, let's take a look at this applet in the next video.
I'll give you a moment to ask questions and also check out the link. All right. All right.
Hi, everyone. We're continuing with lesson 25 on confidence intervals for population parameters. For example, let's say our TA Igor wants to give a confidence interval for the population mean mu of the test scores for a big lecture hall class. And we ask Igor, well, what's your interval estimate for mu? And Igor says, I'm getting an interval between 70 points and 78 points. These here are my limits. And then we can ask Igor, how sure are you? How confident are you that this interval will contain the correct value for mu? It's like answering a big question. How confident are you that this interval will contain the true value for mu? Again, people like Shrilla don't like saying that mu falls anywhere. Mu is. For example, mu may be right here. Mu could be right here. And the question is, does the confidence interval contain it or not? And we may not know until all the tests are graded. In some applications, we never know what mu is. And when we ask Igor, how sure are you? How confident are you? Typically, Igor will say 95% because that's the standard confidence level for a confidence interval. Remember that a confidence interval is an interval estimate where we attach a confidence level. This is related to the old game show, Who Wants to Be a Millionaire? A phone a friend would be asked, how sure are you that this option is the correct answer? And this was before people just looked up everything on Google for everything. They stopped that phone a friend stuff once they realized everyone was just looking up stuff on Google. Then they went to a 50-50. Anyway, let's go to an applet now. To simulate what I was talking about over here, the idea that if you have a bunch of colleagues who want to know the mean IQ for an American adult, who have 100 different studies and they have 100 different confidence intervals, if they're all 95% confidence intervals and they're all appropriately constructed, then about 95% of them will contain the true value for mu and about 5% won't. Let's demonstrate that. This is the excellent Rosman Chance Applet collection from Cal Poly San Luis Obispo. Chance is named after Beth Chance, who's a professor up there. She's the one who really designed these applets. All right, now instead of a confidence interval for a population mean mu, let's do confidence intervals for a population proportion p. For example, a magician's coin. You're given a magician's coin and you test it out. You want to estimate the probability the coin comes up heads by flipping the coin 100 times. And then based on your sample results, you can develop a confidence interval for p, the true probability that the coin comes up heads. Later on in this course, I'll show you how you can construct such a confidence interval. But this software will do it for us, this applet. All right. Now, actually, this thing's going in reverse. Remember, let's assume that we know the actual value for p. Actually, Professor Rosman preferred using pi instead of p since we use p for so many things. But let's say that the true value for p, the true probability of heads, is 0.5. So that, in fact, the magician's coin is, in fact, a fair coin. So let's assume for now that the coin is, in fact, a fair coin. And let's agree to flip it 100 times. N equals 100. That's the number of trials. Now, the deal is that if x is the number of heads, then in fact, the number of heads will follow a binomial NP, or in this case, N pi distribution. But remember the deal here. The deal is that as we experiment with this coin, we don't know what the true value for p or pi is. The applet knows that's a fair coin. The applet knows that this parameter value is 0.5, but we don't. We're just flipping a coin and we're constructing confidence intervals and seeing what we get. So let's say that we flip this coin 100 times. We don't know that it's fair, but the applet knows the coin is fair. And in fact, it is a fair coin. Okay, well, let's do our sampling. So here's the deal. Okay, so based on this 100 flips, it appears that we are getting 54 heads and 46 tails. So our sample proportion, p hat, I know that's kind of hard to see, p hat. Our sample proportion p hat turns out to be 0.540, meaning that out of the 100 flips, we get 54 heads and 46 tails. P hat is 0.540. Therefore, by the way, Q hat, the sample failure probability, is 0.460. We'll use Q hat later on, the sample failure probability. But anyway, this is the result of our random experiment. We flipped this coin 100 times. It was, in fact, a fair coin, but we didn't know that. We flipped this coin 100 times. We get 54 heads and 46 tails. So our sample proportion p hat is 0.540, or 54%. Now, we don't know it's a fair coin yet. So if this is all the information we have, our best point estimate, our best guess for what p or pi really is 0.540. We've seen the coin come up heads 54% of the time. So our best guess for the true probability of heads, or pi, is going to be 0.540, even though it was in fact 0.5. And then from using methods we'll see later on in this course, here's the confidence interval that can be constructed. Again, using methods we'll see later in this course. So if I click on it, actually, we can see, I'm blowing this up a bit, we can see that this confidence interval is going from 0.442 to 0.638. So we're saying that there is these are 95% confidence intervals, by the way. The confidence level here is 95%. So the claim is that given this sample data, there's a 95% chance, a 0.95 probability, that the true value for p or pi, which we don't know yet, the applet knows it, but not us, we're saying there's a 95% chance, a 0.95 probability, that the true probability of heads on this coin, p or pi, is between 0.442 and 0.638, between about 44% and 64%. Now, it turns out that since this was, in fact, a fair coin, which the applet knows, but we don't, since this was, in fact, a fair coin, this commonest interval is good in the sense that the CI does, in fact, contain the true value for p or pi, the 0.5. It is between 0.442 and 0.638. I'll do some erasing here. But now, what if we try out some other intervals? Let's play around with this applet. Okay, let's try it again. Let's reset this. Let's try it again, sample. This time we get 46% heads. Here's our CI from 0.362 to 0.558. Again, it contains the 0.5. So it, in fact, turns out to be a good confidence interval. Let's try it again. Okay. Well, we get back to 54% again over here. I don't want to waste your time. All at once, let's do 100 confidence intervals. Let's say that we have 100 people replicating the same experiment. 100 people flipping, I guess one by one. They can't go all at once. One by one, these 100 people flip this magician's coin 100 times apiece. They each get a sample proportion of heads, and then using the same statistical method, which we'll see later, they construct a 95% confidence interval for the true value of p or pi. To keep things fair, it has to be the same confidence level, the same type of confidence interval for all 100 people. So let's do this 100 times. First of all, I should reset this. Okay, 100 times, 100 people replicating this random experiment. What do you think you're going to see? You're going to see 100 confidence intervals. Let's see what happens. Look at that. This, by the way, is the most recent sample, what the 100th person did. That person got 55% heads. We're not so concerned about that. I want to look at the big picture. These are the 100 confidence intervals produced by these 100 people when they flip this coin 100 times. It turned out to be a fair coin. Now, by the way, if you look at each of these confidence intervals, that black dot in the middle indicates the point estimate, p hat, the sample proportion. So for example, for the very top one, the confidence interval went from 0.452 to 0.648. The point estimate should be right at the midpoint there. Okay. Well, that first confidence interval was good. In fact, almost all of these are good in the sense that they contain the true value for p or pi, the 0.5. What in fact happened? 96 out of these 195% confidence intervals contained the true value for p or pi, the 0.5. So 96% of these confidence intervals did their job. They contained the true value of p or pi. But 4 of these, 4% of them failed. For example, this guy, this one in red. So for this one, you can see the sample proportion was 0.400, only 40% heads, only 40 heads and 60 tails on this experiment for this person. So the CI was rather low. It only went from 0.304 to 0.496 with 0.4 at the midpoint. But notice here, this falls a bit short. Really blowing it up. Well, you have to blow it up quite a bit, but the 0.496, that falls short of the 0.5. This confidence interval in red will not contain 0.5, the true value for p or pi. So this confidence interval fails. Now, this doesn't necessarily mean that that person didn't know statistics or that the coin was warped by the time the person got it. It may have just been bad luck. It may have just been bad luck that this person just had bad sample results. There were 3 other people in the same position. And once again, for these 95% confidence intervals, notice that 96%, about 95%, contain the true value of p or pi, and about 4% failed. Now remember, it's not perfect. I claim that about 95% of the confidence intervals would contain the true value 0.5, and about 95% did. In fact, here, 96% did. Let's redo this experiment. We can tell the 100 people, hang on, let's do it all again. Let's get another set of 100 confidence intervals. Let's do another sample. This time, for, you could say it's a sample of 100 confidence intervals, only 89% of them contained the true value of P or pi. So we had a much smaller success rate here. Let's try it again. Here, 93% of these CIs contained 0.5. Let's try it again. Let's keep trying it. Oops, let's go back to 100. 93%, let's try it again. 95%, okay, so this one was really on the dot, but it didn't have to be. 92%. Actually, what if we keep building things up? Let's not reset it. Let's keep increasing the sample size. Well, the sample size of confidence intervals. Okay, so here the running total, 200. 185 out of 200 of the confidence intervals contain the 0.5. So this here, 185 out of 200, that's 92.5%. Let's keep doing this. 100 more people. 100 more people. 100 more people. Look what's happening. Boom, 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 boom. As we keep doing this, notice that our percent so far of these confidence intervals that contain the 0.5, it's getting closer and closer to the 95%. It's like the law of large numbers. By the way, over here, let's reset this. Okay. Looking over here, this here is a histogram of the 100 sample proportions, basically these black dots that are at the midpoints of these confidence intervals. This histogram collects the black dots. And the boxes here in red correspond to the confidence intervals that fail us. Here there were 6 confidence intervals that failed us. We predicted 5 or 5%. You can see here these 6 boxes correspond to the 6 values of p hat that led to these confidence intervals that were too far off. These ones were at the low end, so it's got to be this guy and this guy. These 4 were at the high end, so this guy, this guy, this guy, and this guy. So you might want to play with this Applet collection. I'll send the link. All right, so more confidence intervals and interpretations in the next video.
Any questions? If you play with this applet, I think we'll get a good sense of confidence intervals. Any questions? Any questions? And even the success failure rate, that's subject to sampling error, right? Questions? Cool stuff. Last video.
Hi, everyone. We're finishing up lesson 25 on confidence intervals for population parameters. So leaving the simulation here, also bear in mind that we can sort these. So these are the most recent 100. We could sort these by their sample proportions. We can see the bad ones at the top and at the bottom, in fact. But we could do it again. Sample, sort. We have a bunch of bad ones here on top, a bunch of bad ones on the bottom here. And actually, if we had a histogram for the sample proportions for all 2,000 or so confidence intervals, if we could actually get a histogram for that, we could probably figure out a 95% confidence interval just from this simulation. If we had 2,000 confidence intervals and their sample proportions to look at, together the middle 95% of sample proportions might form a good confidence interval for P. 95% confidence interval. This is a key idea behind the bootstrap, the idea of using simulations to develop confidence intervals. In which case, have a bunch of simulations. Maybe you don't have to know that much theory. Run a bunch of simulations and look for the middle 95% of sample proportions. All right. Now, back here, about 95% of these contain the true value for mu or P, the population parameter, for a 95% confidence interval, but about 5% will fail. Again, statistics predicts its own failure rate. This failure rate we refer to as alpha. And the confidence level is the complement 1 minus alpha. So, for example, the standard confidence level is given by 95%, or 0.95 as a decimal. So the value for alpha is the complement, 1 minus alpha. Okay, so 1 minus alpha is 0.95. The complement of this is just alpha, which is 0.05. 0.95 and 0.05 are complementary probabilities. They add up to 1. So if there's a 95% chance that a confidence interval contains mu, then there's a 5% chance it doesn't. This notation for alpha, we're going to see later on. It corresponds to the probability of us basically failing. It's the probability of us basically failing, as we'll see when we get to hypothesis testing in the last part of the class. Okay, now let's compare confidence levels. You might argue, well, why don't we get a 100% confidence level? Why not get a 100% confidence interval? Well, what impact would that have on the confidence interval? So let's say I have two interval estimates, and they're both centered at the sample mean, x bar, from a sample. And we want to estimate mu, a population mean. Again, these are both interval estimates, symmetric about the sample mean. Which one of these is more likely to contain the true value for mu? The smaller interval on top or the wider interval on the bottom? Imagine a shooting range. If you're at a shooting range and you're trying to hit a target, they're both centered at the same place. How are you more likely to hit the target? If you're shooting a wider swath of bullets or a thinner swath? That's a more violent example or analogy. Well, you're more confident that the interval contains mu if it's wider. So we associate wider confidence intervals, assuming that they're all centered at x bar. If it's out here, well, that's not too good. But if you have interval estimates that are all centered about the sample mean, then the wider one is more likely to contain mu. But that leads to a trade-off. So confidence levels and trade-offs. Based on the same sample data, we can use different confidence levels, for example, 95% versus 99%, to construct different confidence intervals, a 95% CI versus a 99% CI for mu, or some population parameter. Again, which is usually more likely to contain a population mean, a wider confidence interval or a smaller one? Again, assume that they're both symmetric about the sample mean. They're both centered at the same place. Well, a higher confidence level, like 99%, will lead to a wider confidence interval. So for example, up here, if I told you that one of these was a 95% confidence interval for mu, and the other was a 99% confidence interval for mu, based on the same sample data, well, the top one would have to be the 95% one, the thinner one, and the wider one would have the larger confidence level, 99% or 0.99. So again, the 99% confidence interval here is more likely to contain mu than this thinner 95% confidence interval, and they're both centered at the sample mean. Again, the same is true for p hat and p. A higher confidence level will lead to higher reliability. This 99% confidence interval is more likely to contain mu, but it's wider. It has lower precision. Now, you may not appreciate what this all means. Let's put this in the context of students asking about test scores. So forget about this whole thing about means. Let's go back to the general idea of confidence levels. So if you were to ask me, Professor, could you give me a 100% confidence interval for what I did on the test? Let's say the test was scored out of 100 points. What's the only answer I could give you? The only answer I could give you is from 0 points to 100 points, assuming no extra credit or anything, and no negative scores. Let's say I'm not super cruel. But if you were to ask me, give me a 100% CI for how I scored on the test. Well, there you go, 0 points to 100 points. You agree that's correct. You're absolutely sure this contains your score, but are you going to thank me very much? Well, probably not. This only tells you how much the test is worth, what the maximum score is, right? Maximum possible. It doesn't tell you how you did. This just tells you that on the test, you could possibly score between 0 points and 100 points, but I'm not really telling you how you did at all. I'm telling you nothing about how you did. You have no idea if you got an A or an F. So let's say you go, okay, you're being very reliable, but not very precise. So again, this 100% confidence interval is reliable, but not precise. So let's say you ask me to give you a more precise confidence interval. And I tell you, okay, I think you scored between 78 points and 82 points. And you go, wow, that's pretty precise. I feel very good about my knowledge about how I did on this test. You're telling me I scored between 78 points and 82 points. How sure are you? It's that who wants to be a millionaire question. How sure are you? And I tell you, I'm 10% sure. I'm giving you a 10% confidence interval. So here, I'm being very precise. I'm giving you a very thin swath of numbers, a very thin swath of scores, but, so it's very precise, right? I'm being very precise here, but it's not very reliable. There's only a 10% chance that you're in here based on appropriate methods, whatever that means. So there's a trade-off between reliability and precision. And again, the classic trade-off is 95%. That's the standard. 95% is the gold standard. That's the typical trade-off we have between these two issues, between these two tensions of greater reliability versus greater precision. So very often I'll ask about 95% confidence intervals, but not always. I reserve the right to ask about other confidence intervals as well. Reliability versus precision. You can't get everything in life. Later on, some more lessons in statistics.
All right, so that's lessons 24 and 25, and later on we're going to talk about how to construct these things, right? Yes, there's software, there's Excel, okay, but these are the principles of point and interval estimates, in particular confidence intervals. All right, so we're at 8:36. I'll stick around for questions, but those are the ideas for today. Any questions? Otherwise, thank you. Have a good night. Okay, I will stick around for questions. I know we're just starting part 4, but I don't know, maybe there's some late homework, whatever. Any questions? That's the class. I will stick around for questions. All right. Okay, so I'll pause. We're approaching 9:38. So I'll come back at 9:40, see if there are any questions. All right, so let's pause. 9:40. I'll come back, check on you.